Hi everyone, I am Jiaji. I'm presenting for my project about direct planning for a two-bar linkage. Deformable objects such as cables are highly underactuated. Imagine on a 2D plane we want to move a cable from an initial pole to a goal pole. What we could do is use multi-bar linkage to simplify and model the cable, so here I use a two-bar linkage. Manipulating the cable can be simplified as heavy actuation force is applied on the object. So in this project, I put two actuation forces at the center of the mass of the upper bar. With this setup, we can do trajectory planning for the underactuated system. It's pretty easy with the methods we learned in the class. However, once there is an obstacle in the way, the trajectory planning is no longer trivial. Common methods include using collision-free constraints or manually decide the contact sequence. For this project, I want to see if I can let the algorithm to decide if it wants to contact with the obstacle or not, to implicitly plan for contact strategy with the methods learned. Let's come back to this simpler problem. I tried both optimization with hand-written equation of motion and the direct collocation with your defined system. After adding constraint for the initial and the final state, acceleration force limit, and set the cost to be quadratic, both methods successfully solve it and the result seems great. However, both methods discretize the dynamic, which will cause error. And due to numerical error, if we directly input the force trajectory to simulation, we can see the error in the states grow as time proceeds. The result shows that the local controller is needed. I add a finite horizon LQR here to keep the actual state close to the nominal trajectory generated from the direct collocation. And with the feedback controller, we can see the actual states overlap with the nominal trajectory perfectly. So now it's time to look at the trajectory planning with obstacle. The method I picked is iterative LQR. In Drake, I set the collision property for all the objects to be hydroelastic contact, and for the ILQR, the initial guess for the policy is readily generated. I first verify the ILQR method for the case where there is no obstacle in the system. It converges fast and works perfectly, as you can see. Next, I add the box to the system and set the stiffness of all the objects to low. We can see contact and penetration happens at time around 3 seconds. But the algorithm manages to find a trajectory to the goalpost, and it also managed to avoid large penetration to lower the acceleration force. However, if the stiffness is high, the solver just gave up and failed to find a successful path. One potential explanation is that the random initial guess leads the two-bar linkage to the obstacle, and in that region, staying there and not moving might be a lower cost trajectory due to the high stiffness. Thus, the algorithm is trapped by that local minima.